Hello everyone. Today we're going to introduce you a small hydraulic system model, which is called hydrostatic transmission. Our learning objectives in this topic are following. We will present how to build a hydraulic system model from the schematic of a hydrostatic transmission. Then we will analyze the simulation results, more specifically, why there is cavitation happen in this model and how to avoid it. From this schematic of a simple but meaningful hydraulic system, you can find all fundamental and critical components. There is tank at bottom, which is used to provide the required fluid and collect the fluid again after flowing inside the complete circuit. Then the pump is used to provide hydraulic power by absorbing the fluid from the tank and feed it into the motor to drive the rotary inertia as load. A pipe is also shown in this schematic to remind us we should consider the influence of it. Finally, there is a relief valve, for which you can always find in hydraulic system schematic. If the operating pressure exceeds the safety level, the relief valve will open and let the fluid flow back to the tank. To parameterize the system model, all important parameter values are provided here. For the rest of parameters, we can leave them with default values. From HYD library, select the components as shown in the MC model in this slide. The fluid property is set with elementary option. Based on the parameter values shown from previous slide, we can input them directly in each component. Please note, for the pipe component, you need to first switch to submodel mode and click the direct line. Then you will be able to select a different hydraulic line model for this pipe. Please make sure you use the line submodel named HL40, which will consider only capacitive effect. For simulation setting, we will use the default option. After a simulation run from 0 second to 10 second, let's check the results of shaft speed of pump and motor. You can find the speed signal of motor vibrated at the beginning and then stabilized at 1500 rpm. As the rotary load has inertia effect, this will cause the system pressure when to zero level, as shown in the plot on the right-hand side. So what's happening in the network? It's cavitation. Because the motor rotates faster than pump, which means the provided fluid is not enough to drive the motor or the rotary load, and it will cause pressure drop down, and eventually leads to cavitation phenomena. This is not allowed in the hydraulic system, otherwise the pump will be damaged in this situation. So to avoid cavitation in this system, we should impose a continuous pump start profile, as shown in the plot below. The speed input is now a gradually increased signal after introduction of a second-order lag component. Let's make slight modifications on the pipe submodel and check what could be the impact on simulation results. First, let's update the pipe dimensions with new geometry. Then to add resistive effect in these two pipes, please select HL0001 and HL0003 for pipes. In fact, there is no difference between these two submodels, only input and output requirements are different. The resistive effect is like the friction applied on the fluid. So from the schematic at bottom of this slide, the friction effect is represented by a shaded area between two volumes. So as long as there is fluid flowing through the pipe, there will be energy losses, and pressure level will be decreased. Once you updated the pipe submodel successfully, perform another simulation run. Then we observed that there is pressure drop between pipe inlet and outlet due to introduced resistive effect. Then in second step, we will introduce inertia effect in both pipes and check the results. Please select the submodel HL0042 for pipe 1 and HL0040 for pipe 2. Now compared to pipe submodels from previous slides, you may already notice that except for capacitive effect, which is considered in the circles, and the resistive effect, which is considered as shaded area, there is rectangles inside the shaded area. These rectangles are equivalent to fluid inertia, and usually for long and thin pipe, you could consider it into several sections for more accurate calculation. After launching a new simulation run, The results seem quite similar after we add the inertia effect. But if you zoom in at starting phase, you can observe the pressure at pump outlet has strong vibration after introducing fluid inertia effect. This is more realistic compared to previous two submodels, but of course at cost of CPU time. And if you don't have corresponding test data, such as pressure, flow rate, etc., to validate this model, then usually it's not recommended to use such detailed model. Let's summarize what we've learned from this short lesson. Now we can build a hydraulic system model with all fundamental elements, such as pumps, pipes, valves, tanks, and motors. Moreover, with different submodels we can have more detailed or less detailed results, depending on the physical phenomenon considered. So choosing a proper submodel is to be memorized when you're going to create your own MSIM model in the future. With this, we end our lesson on hydrostatic transmission. Thanks.